what I'm going to do is basically give you a bit of a highlight of our recent research work. The title sort of gives away what we're trying to look at. What this is a project where we basically are looking at aspects of fundamental cosmology about the universe that we sort of live in. And I think it's taken for granted probably by most astronomers that we live in an expanding universe, and it's described by Einstein's relativity, but there's still a few corners of academia where that's not fully accepted, right? That the picture that we live in an expanding universe is somewhat, they say that we're being misled by the evidence and our universe is actually doing something different. So the topic that we're going to talk about is this notion of cosmological time dilation, the fact that we should expect to see the distant universe run in slow motion, and in particular in a class of objects, these objects known as quasars, because they've proved problematic with this particular phenomena over the last 3 to 4 decades. This is the kind of picture that we get in all of our cosmology textbooks, right? So we know that way back in the early 1900s, Einstein wrote the general theory of relativity. And through the 1920s, we had people like Lemaitre and Friedman working on the mathematical description of the universe, and they said that mathematically we should expect our universe to be evolving over time, either expanding or contracting. And of course, Einstein wasn't particularly happy with that picture. He thought the universe should be static and unchanging. But at the end of the 1920s, we had the work of Edwin Hubble, who was looking out at galaxies in the universe, and he found that galaxies were moving away from the Milky Way, and that there was a particular relationship between how far those galaxies are and how fast they are moving, right? So what we have got is we've established that from the observations and from the theory that our universe is expanding, and what that does is that when we look at a distant source, what we say is that the light from that source, as it's traveling through the universe, that light gets stretched by the expansion of the universe. So objects appear redshifted, which we can interpret, of course, as a velocity, as a Doppler shift. And there's a particular relationship between distance and how much redshift that we see. And just to illustrate the fact, they work now. So this is, of course, the picture that Hubble published back in 1929. This experiment has been repeated many times, of course. What we've got across the bottom here is distance in parsecs, velocity up the side in kilometers per second. Hubble, when he started his measurements, he had no real preconceived ideas about what the universe was doing. I think there was an expectation that galaxies are basically moving around at random. And so you'd expect half the populations of galaxies would be coming towards us, half would be moving away. And what he found instead, of course, is this very distinct relationship that the further away the galaxy is, the faster it appears to be moving from us. All right? So this is taken as essentially the birth of modern cosmology. And I guess one aspect of this that's not fully appreciated is that Hubble himself never really took to that explanation that we live in an expanding universe. He wasn't very happy with the overall picture that we lived in a dynamical universe, thought that something else was going on, but people were convinced by the mathematics that we've got that had this prediction that more distant galaxies, the larger the redshift that we get. So let's just think a little bit about what the redshift means, of course, right? What we're talking about is we're taking photons of a particular wavelength, and what we're saying is that as those light rays travel across the universe, their wavelength is getting larger, so their frequency is dropping. So if you can just imagine that we were looking at the source of the photons, right? And you can think of a photon source essentially as a little oscillator going up and down at the frequency of the light. So if we are seeing light that has been redshifted, what that actually means is that if we can see the oscillator, that must mean that the oscillator appears to be moving at a lower frequency than if we were in the rest frame with that oscillator. So people realize that there's a flip side to this redshifting of photons, and that is that we should expect a cosmological time dilation. That when we look out into the universe, we should expect to see the distant universe run in slow motion compared to the universe today. And this was realized quite early on. So this paper was published back in 1939 by Wilson. And essentially what what Wilson had noted is that there are variable sources in the universe that we can use effectively as standard clocks, right? There are things that have timescales associated with them, and his particular focus were cosmological supernova, distant supernova. So these are exploding stars, of course, and they explode, they brighten, and they fade over some characteristic timescale. And what Wilson pointed out is that due to this time dilation effect is that if we look at supernova out into the universe, the more distant the supernova, the longer it should take to brighten and then fade. Okay? So predicted in 1939, it just took another 80 years until we were able to measure this effect. Okay? Now, the reason is that whilst this is, again, it's a theory paper, right? In theory, this is simple. But then physics gets in the way and makes everything harder. And the problem that we have in this particular idea is that not all supernovae are identical. Okay? So we already know that astronomers discovered the first set of supernovae, and then you do what astronomers do, and you start to classify things and put them into boxes, and you have a type 1 and a type 2 and a type 1a and a type 2c, and you realize is that there are differences in the supernova. And that means that the thing that you're looking for, which is your characteristic tick between each of these supernovae, is going to be different because the physics of what's going on in each individual supernova is going to be different. But we have a very well-defined prediction for what this should look at, right? What this should look like. So this is basically our time dilation factor up the side here. This is how much slower we should expect the distant universe to run. And what we have got is that this term here, it should be directly proportional to 1 plus the redshift. Okay, so if we see an object at redshift 1, it should be running at half the speed compared to an object in the local universe. Of course, we can map that redshift onto look-back time. So this is now looking back towards the Big Bang. And what we can see is that as we look further back into the universe, that we get more and more of this cosmological time dilation. So I think it's important to remember that there's a couple of different things in here. So this relationship here, that the time dilation that we get, being proportional to 1 plus z, that is the fundamental prediction of our modern cosmology, right? So this prediction doesn't care what kind of stuff we have in the universe, doesn't care how much matter there is, how much radiation, how much dark energy, or whatever mix you want to put into the universe. Whereas mapping onto our look-back time does. So this is where, that modern cosmology where we talk about the makeup of the universe, that goes into this part. If we don't see this cosmological time dilation effect by looking at distant sources, that sort of is worrisome for the mathematics that underpins all of modern cosmology, right? It's one of those fundamental predictions, irrespective of what our actual makeup of the universe is. So, as I mentioned, it took 80 years until people were able to do this measurement. The reason is that, again, I started as a grad student a very long time ago. And when I was a grad student, one of the biggest arguments was, what is the Hubble constant? How fast is our universe expanding? And it was still not far off that regime where there were two camps, one saying it should be around 50 kilometers per second, the other saying it was around 100 kilometers per second. And this had a big impact for the measurement of the age of the universe, right? So it was decided, once Hubble was launched in 1990, that one of the key projects involved with Hubble would be to nail down the Hubble constant, to understand how fast our universe was expanding. And to do that, what they would do is they would focus upon cosmological supernova. So here we've got an illustration of a supernova here. So that's this bright dot there. So this is a single star in that distant galaxy. For a period of around 2 weeks, that individual star, which has exploded, will outshine the light of all the other stars in that galaxy put together. So this is the reason why we want to focus on supernova, is that they're very bright and we can see them out to cosmological distances, but to use them to measure the Hubble constant and then to measure the makeup of the universe, you need to use supernova as standard candles. You need to know how intrinsically bright they are. So what happened into the 1990s and then into the 2000s is there was an immense amount of work that was done on calibrating a particular population of supernova. And the focus was on supernova type 1a. And so these are supernova whereby you have a white dwarf and a stellar companion. You get this mass transfer onto the white dwarf. Eventually you go past some critical point and the star receiving the mass explodes in a supernova. So what you've got there is essentially a very sort of fine triggering mechanism that once you've passed a certain amount of mass, your star goes bang, and you hope that each of those explosions would be essentially the same. But of course, they're not. They are very, very similar, but there are differences between each sort of supernova type 1a explosion. So in here, what we've got is, this is a bunch of supernova light curves. Here's time in days, here's brightness, and these are all supernova type 1a. And what you've got is that they've all got very similar kind of curves here for their brightening and fading, but there's still a dispersion in the population. And that dispersion comes down to all those other factors that we have, metallicity, properties of the orbits, all that kind of stuff that comes into calibrating populations. And this is what a lot of people spent a lot of the 1990s doing, is calibrating these to put all of these individual supernova onto the same footing, right? And the result, of course, was this particular picture. So firstly there was the measurement of the Hubble constant, so you can measure how fast the universe was expanding. Then what people set out to do as part of the cosmological supernova project is to measure the apparent brightness of supernova versus their redshift. Okay? So these are the data points here. And what you've got, of course, is that this relationship between redshift and brightness, that depends upon your cosmological parameters. So that depends upon whether you live in a flat universe or an open universe or a closed universe, or there's this much matter and that much radiation and that much dark energy. So this was what people did. They measured supernova out to just beyond redshift 1. They find the best curve that goes through that data. And the expectation at the end of the 1990s was that we live in a universe which is decelerating. Right? They thought that there's matter in the universe, that's going to grab onto the expansion and slow down the expansion. Of course, at the end of the 90s, what they found is that this predicted that the universe is actually accelerating. And what it showed is that the dominant energy component in the universe is actually dark energy, which is causing the expansion of the universe to go faster and faster. So this kind of picture, this got Brian Schmidt and Saul Perlmutter and Adam Rees the Nobel Prize back in 2011 for the discovery of the accelerated expansion and dark energy. But as well as this, what they have done, of course, as I said, they put all of the supernova onto an equal footing such that they've all basically got calibratable light curves, which means that you can now do that experiment whereby I can take the time scale in my supernova explosion, use that as my cosmic clock, and see if I can measure the cosmic time dilation effect. So this was done over the last couple of decades. This paper is quite recent, right? This is 2018. Very little fanfare. After you discover dark energy, who cares about this kind of test? But what we have got here, this is 1 over 1 plus the redshift. So this is effectively the scale factor of the universe. So 1 today means today. As we go down here, when it's 0.5, the universe was half the size it is today, right? So this is scale factor here. And then this is aging rate. This is how long this is the factor that comes in that tells you how much slower a supernova light curve brightens and fades as a function of the redshift. So these are all the local supernova, which they use for local calibration. You have to pin everything to the local universe. This is their kind of time scale that you have. And then as you go out into the distant universe, you find that these supernova are going slower and slower and slower. And of course, that's good, but that's just part of the story. If you want this to agree with your fundamental cosmological ideas, it can't just be fainter as you go to high redshift. It has to have that particular relationship. Sorry. It is the time it takes for a supernova to explode in the local universe divided by the time that it takes in the distant universe.
Does the time mean like time to the peak from the rise or something?
Yeah. They set a time scale, right? So they have a certain amount of the rise time and all the way to the fade off by some factor. So they basically just try and put that, like, we're going to measure a property of all the light curves that we can compare and just use that as a tick.
Maybe a follow-up. So when you rescale supernova like this with the Phillips relationship, that's like a scaling in like a time.
Yeah.
So isn't that degenerate with this, or how do you?
No, not completely. I mean, so the Phillips relationship, it basically is the one that does that adjustment to put them all on the same thing. Then this is the 1 plus Z effect, which is on top of that.
And they don't interfere with each other.
That's what they tell us. We trust the supernova people, right? Yeah, good. So the important thing is not just that you have this relationship with redshift, but it has to be a particular relationship, right? The aging factor has to be proportional to 1 over 1 plus Z, and that's what this line is in here. And that's the best fit. Everything basically works, right? So as I mentioned, this is 2018. There were earlier measurements with smaller samples of supernova, but again, very little fanfare because everyone went, yeah, this is just the way we expect the universe to be, right? So it's a cool result, though. The problem is that supernova are not the only luminous and variable objects in the universe, right? So there are other variable objects out there, and we should expect them to show the same kind of relationship between redshift and how rapidly the variability goes. And one of the key focuses are these objects, quasars. So quasars are highly luminous objects. So they're supermassive black holes, millions to billions of times the mass of the sun. They have an accretion disk of matter, so that matter falls in, gets very hot, swirls around, is very, 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 very bright. So we can actually see quasars effectively as far as we can see in the universe. So out where we see the most distant galaxies, we're also seeing distant quasars out at redshifts 5, 6, 7, etc. Quasars are variable, right? If you imagine their accretion disk, okay, it's material swirling around, it's a hot plasma, there's magnetic fields, all those things that we hate to calculate, stuff basically, popping off. And so you basically see that the luminosity that you get is going to vary on some time scales due to all of the different physics that we've got going on inside this small region near the black hole. So what we've got, people have monitored quasars for quite a while. This is just some relatively recent light curves that people have got for relatively nearby quasars. And so you can see that there is a whole bunch of variability in here. Some of it is quite long scale variability. Others is quite short. So you've got these quite peaks, things going up and down. So the question is, can we use these as standard clocks and measure the cosmological time dilation effect, right? So we expect it to be there. And as I mentioned, people have tried to do this and have generally just failed. So the story starts at some level, but not quite. There's a whole bunch of people working on this, but there was a paper by Mike Hawkins back in 1993 which really kicked off the modern discussion. So Mike, I don't think this is actually Mike himself, but you can tell this is an older picture of an astronomer. This is the UK Schmidt telescope up at Siding Springs, and the UK Schmidt telescope, wide field telescope. You could put photographic plates at the focus. You could get images of large patches of sky with these photographic films. So Schmidt telescopes are well known for surveying the sky with photographic films. It's a real pain to take photographic films and work with them. So what people did is you get your film and then you scan it with a laser scanner. And there was one in Cambridge and one in Edinburgh where Mike Hawkins was based. And you can identify galaxies and stars and other objects. So what Mike was doing when he was working with the UK Schmidt is that every so often he would return to the same fields and image those regions, and he identified quasars in those regions, right? And he was able to produce very long-term light curves on the variability of these quasars, right? So you got 1975 up to about 1995 here. Because he wasn't at the UK Schmidt all the time, you can see that these are separated by 6 months to a year, right? But you have definitely got quasar variability going on. So Mike basically published this stuff back in 1993, and his conclusion is that in his sample he had a whole bunch of quasars. Some are low redshift, some are high redshift. And when you looked at the properties of their variability, there was no difference between the two. And I don't want to go into the details of the statistics, but the key thing is that if you just focus on this panel, this is just a power spectrum. You know, you get a time series, you take a Fourier transform. What else are you going to do? So here's frequency, here's power spectrum. On here, you've got your data points for low redshift and high redshift quasars, and the curve goes through both of them exactly the same. And so either there is a conspiracy such that high redshift quasars vary in such a way that basically opposes the cosmological redshift effect, such that they look the same as low redshift quasars, or there's something else going on. So Mike has been publishing this kind of work now since 1993, and his results always come back that he does not see a cosmological time dilation effect. He's not the only one, but he has some of the longest timescale data. Fair enough, that might be an observational issue, but then, of course, you have to propose why you don't see the expected time dilation. So Mike's suggestion was the thing that got a few people kind of angry, is that quasars don't vary. All right? So Mike's suggestion is that quasars are actually distant objects. They're intrinsically luminous, but they don't vary. They're just bright points in the universe. But we see quasars vary, so you need to introduce variability through some other means. And his suggestion is that one way you could do that is by filling the universe with black holes. Okay? So say all the dark matter is in the form of black holes. They all whiz around the universe, and they pass in front of our distant quasars. And each little black hole has a microlensing effect. It magnifies the quasar. And what you get is a resultant variability, which is, of course, got nothing to do with the quasars itself. So it's not tied to their redshift. It's to do with the fact that there's a population of black holes between us and these distant objects. Now, I said, as you can imagine, the people who work on quasars, who say that, yeah, we think they're black holes and accretion disks, etc., they should vary, they weren't particularly impressed with this. And in fact, I was there at the time, the astronomer royal Martin Rees, who was one of the ones that proposed that quasars are relativity accretion disks, said he would eat his hat if Mike Hawkins was correct. Right? So, okay, but that's fine, right? This is a scientific paper. It's published in a journal. This was the '93 paper was published in Nature, so it has to be wrong, right? No, I can't say that because my paper was published in Nature. No, This was published, so it's of course up to the rest of us. You know, is this correct? What tests do we do, etc., etc. Except there is a minor issue, right? And that minor issue is that it's not just us astronomers that read papers. Okay. So Mike published a paper back in 2010 when he published his latest results, again saying that there's no time dilation in distant quasars. Okay? And that's when the media got hold of it. Okay? So this is physorg.com. This is New Scientist. Right? You can see what the headlines say. And you can see there's a little sub-headline here. Is the Big Bang Theory wrong? Now, if you delve into the darker regions of the internet where they discuss cosmology, and I have been there, one of the prevailing things is that there's a feeling that modern cosmology is essentially a lie, right? That essentially this notion of expanding space and an evolving universe, it's all wrong. That's not the right picture. And you sort of say, but there's all this observational evidence, and what people say is, aha, but quasars, right? Quasars don't show cosmological time dilation. And people have proposed, these are not necessarily members of the public, there are people at the edge of academia that make these propositions as well, is that quasars aren't cosmological objects, right? They're actually very luminous objects in the nearby universe, right? The redshift that we see has got nothing to do with their cosmological distance, because cosmologists are idiots, right? And so, you know, we've all drunk the Kool-Aid that redshift is related to expansion. And again, that there's a proposal that quasars are fiery objects ejected from local galaxies and all this kind of stuff, right? It exists there in the literature. Okay? I think Arp was one of the ones that proposed that quasars are actually local objects that have been ejected, right? He was a reasonably mainstream astronomer. Okay? But, so fair enough, this is what goes on. But we have to ask ourselves the question of, you know, why aren't we seeing this time dilation in the data that Mike's getting, right? It's a lot of data. What's missing? And so we have to sort of ask ourselves questions about the data itself. Okay. So we've got data which is, like I said, 20 odd years there. Is that sufficient? Is that sufficient to identify a particular characteristic in a quasar sort of light curve? And is the sampling, right? Is that just too poor to pick out the features that we would hope to use again as a tick? And the other problem that we have is actually very similar to where the supernovas people were back in 1939, and that is the fact that quasars are not identical objects. Okay, so there's a couple of things that we need to worry about. Number one is that they come in a whole range of different kind in terms of their black hole masses, from millions of times the mass of the sun up to billions of times the mass of the sun. So the physics of those guys are likely to be kind of different. The other problem that we have is that the luminosity that we see from quasars is right across the spectrum. High energy stuff comes from the inner region. Low energy stuff comes from the outer region. So you might expect that the variability that we get in high energy radiation from a quasar will be different to the variability we see at low energies. And of course, we have to remember that if these are at cosmological distances, then what rest wavelength you're observing, okay, will depend upon the band that you're looking at and the redshift of the quasar. So if you're looking through our band and you've got quasars at different redshifts, you're not looking at the same part of the accretion disk in each of those quasars. So maybe that's the problematic issue. So things changed, at least for me, at the end of last year with this paper that was published by Zachary Stone in the US. So what we have got here is a large number of people, because it's a project over a large number of years. This is a monitoring campaign of quasars, okay? So this campaign is over 20 years, and it's observing the same batch of quasars that were originally identified in Sloan in Stripe 82, okay, and monitored in the same bands over that period. Of course, what has happened is that the facilities have had to change, telescopes have had to be updated, but what this team wanted to do was ensure that the analysis was putting the quasars onto an equal footing, right? If you change instrument, you want to make sure that if you're reporting a magnitude, you mean the same thing from Sloan photometry all the way over to deck cam photometry. So we've got roughly 200 quasars observed in GRNI 20 years. And the other thing that was realized, and this was only something in the last decade, is that people finally, now they were starting to get very well sampled light curves from quasars, is they realized that they were getting a handle on the statistical properties of what was going on in a quasar light curve, right? So quasars vary. I mean, if they were nice and simple and varied like a sine curve, our lives would be interesting. But they actually follow something that's known as a damped random walk, right? So, it's your drunkard's walk plus there's a time scale in there to return to some sort of characteristic kind of behavior, okay? So this team went through and they analyzed all of these samples of quasars, right? So what we've got here, this is light curve of just one of the quasars in one of the bands. Is a Gaussian process fit to the data. You go through, you say, I'm representing this by a damped random walk. That basically ties your correlation across your light curve, right? It correlates properties of your light curves at different time separations. You go through and you fit essentially all of the parameters. And the key thing is that what we have got is that in our correlation between points that we have in our light curve, we have this term that correlates the light curves at different time intervals, and that has a time scale in it. Okay, so there's a time scale for the damped random walk. Okay, so what we suggested is that we can use that time scale as the tick in our quasar light curves, right? So we can say there's a tick there, and we expect similar quasars to have a similar kind of tick. Right? So if you imagine same mass, same kind of accretion disk, same kind of variability, we're going to get similar kind of light curves and same damped random walk. The problem that we have, of course, is that this sample of 200 quasars is like whatever they could find in that patch. So they're not all the same. They're not all the same mass. They're not all the same luminosity, etc. But they've observed them with enough data that we were able to basically start to group like quasars together. Okay? So what we've got here, this is the entire sample, right? This is a typo, that's ergs per second. So what we've got here, this is the luminosity of the quasar up the side. And then this is the rest wavelength that the quasar is being observed in across the bottom, right? So for each quasar, there are 3 data points. So there's a G, R, and I, and these have been basically moved into the rest frame. So for this particular quasar, got these 3 points here. This one, we're observing it around 6,500 angstroms, 5,500, and 4,000 and something. Okay? So we take all that data, and we basically try and group the quasars together. And so what we've got up here, if we just take this top box, okay, what we're saying is that all the objects in here, they are all of around 10 to the 47 ergs per second. That's their luminosity. So they're all putting out equal amounts of radiation. And we're observing them in this sort of waveband down here, which is in the ultraviolet, in terms of their rest frame. Okay? And we did that. We sort of laid this grid out. And what we said is that we expect that this population in here, okay, should have the same intrinsic damped random walk timescale. Okay? Now, in this particular box, those quasars are at different redshifts. Okay, so there's some at some redshifts, some are further. So there's a population of redshifts in here, populations of redshifts in each of these particular boxes. And so what we're saying is that if they're similar, they have the same damped random timescale, random walk timescale, then the only difference in the observed timescale can come from, if it's due to the expansion of the universe, the cosmological expansion. Okay? So what we did is essentially we tried to represent the variability in each of those boxes by a particular function. We're dealing with a log of the timescale there. So what we're saying is that there is some sort of intrinsic timescale, plus then a term that accounts for a dependence upon redshift. So if n here, this index is equal to 1, then that's the cosmological expectation, right? It goes as 1 plus z. If n is equal to 0, then there's no redshift dependence. And so we're back to that kind of picture that we have with Mike saying that there's no cosmological time dilation in there. So this is what we wanted to test. I'm going to put this up and then see if we can skip this or not. Just to check. Are we all Bayesians here? Yeah? Yes, no? Do we need a Bayesian 101? I gave this talk in Europe and I gave it to the wrong department. They had not, they were not members of the right church.
Part of our HR policies, we don't allow anything, we just...
Oh, okay. I'll just pop this up and just say what we did. So the key thing is that what we wanted to do was test different hypotheses, okay? Which for some astronomers it's like, whoa, what's that mean, right? We've got our data, we've got our model, and we've got that index. We want to ask ourselves the question, what index gives us the best description of the data that we have in front of us, and how does the evidence basically of an index equals to 1 relate to the evidence of an index equals to 0, etc. So what we do is essentially we go through the fun of Bayesian analysis. We calculate what's known as the Bayesian evidence for each of our hypotheses, and then you can have a look at the ratios of the evidence, and you can see what is a better description of the data, sorry, let me just reword that slightly. What values of n give you a better description of the data in terms of the Bayesian evidence? Okay, so that's what we wanted to do. So again, we have this particular formula, and we considered 5 different hypotheses. So our null, our H0 hypothesis, is that n equals 0. So we can fix that and calculate the Bayesian evidence with n equals 0. Right? That's the case where there's no cosmological dependence. N equals 1, that's the expected dependence from our fundamental cosmology. We set n equals as a free parameter, right? So we just saw what does the data say about n. And then we also considered 2 extreme values where n was fixed at -1 and at 2, just to see what the data says. So we go through that. We crank the handle, and we end up with our table. So here's our hypotheses, here's our values of n, here's log z, and anyway, the important thing is the ratio of these things. So what we've got here, the best hypothesis, H1, is when n is fixed to 1. Okay? So in terms of the hypotheses we tested, right, this is the one with the strongest Bayesian evidence. And in fact, it outweighs the case where n is equal to 0 by a factor of around 10 to the 5. Okay? So this hypothesis overwhelms that one as an explanation of the data. Similarly, the cases where we tried the extremes, they are less preferred as well. And when we have n equal to a free parameter, we've got an extra parameter, right? So that acts against you in Bayesian evidence. That's your Occam's razor effect. You added a parameter, so you've increased the parameter volume of which you need to do this integral. But we find that that is a factor of, basically 5 lower in when we allow n to be a free parameter. Okay. What we find, of course, though, is that when we look at our distribution of n that we get for when it's a free parameter, that still encompasses n equals 1 to a very high degree. Now, again, we might not expect n to be exactly 1, because it would be surprising if there was no quasar evolution over, the redshifts that we're considering. But so that might account maybe for a bit of an offset here, but clearly that component that we have in there where our cosmological 1 plus z term is playing a strong part, that's encompassed in what we've got in this distribution. How are we doing time-wise? I can't see a clock. Oh, it's up there. Oh yeah, there is a clock. It's hidden by the light. Okay. All right. Let me try and wrap up. So the other thing is, of course, we've got those other parameters for each of our boxes. We have our C parameter that we had, which is our intrinsic timescale. And so what we've got, these are the distributions. So this is highest luminosity, second highest, third, fourth, just working our way through. And you can see that as we go between each of those boxes, there is a systematic trend across each one, right? So this is telling us that across that space there is quasar physics involved. They do have different intrinsic timescales based upon if they're very luminous and ultraviolet compared to faint and whatever's going on in the red. So this sort of still needs to be deciphered about what this is telling us about quasar physics. But I like cosmology, and I'll let the quasar people sort that one out, right? So, okay, so I'm just going to finish up by putting up the conclusions, right? We basically have a sample of 200 quasars that we've analyzed. We've gone through using the damped random walk timescale. We found that the best hypothesis that we can use to explain the data is that there is this cosmological time dilation effect that goes as 1 plus z. And the thing that's really cool is that the supernova that we observe, we can see those out to redshift 1 and a bit, so which is looking back roughly half the age of the universe. When we see the slowest supernova basically taking twice as long as nearby supernova to brighten and fade. In this particular sample, the most distant quasar is at redshift 4, which means that the distant quasars are taking 5 times longer to do that characteristic variability than the ones in the local universe. So we are seeing basically time run significantly slower in the early universe compared to today. And I should probably finish there, so thank you.
Hey, I have a question about using supernovae to look at the time dilation. I was just wondering, because with that plot where you have the dilation between the super redshifted supernovae and the one supernovae. Has anyone tried to estimate the magnitude that the different metallicity would have on that?
That's part of the stuff that's gone into the calibration of the supernova. So if you are brave, yeah. So again, if you go back to the papers in the 1990s, there are papers like this where people talk about correlating all of the effects of the supernova from the metallicity of the population they're in, the effect of dust, and da. So they've gone through all that, and they claim that they've taken out all of those intrinsic effects, and that we should believe that these supernovae are the same. They've been calibrated to be the same objects. Now, there's still argument from some people that that's not the case, and so this bubbles up in the literature every so often that somebody claims that something in the supernova sample wasn't accounted for correctly, and therefore there's no dark energy multiplier. But normally those disappear because there's just so much on this calibration work.
Other questions?
I was just wondering, with given the the factor of 5-ish in the timescale for variability, if you get your highest redshift quasars and the comparable lowest redshift quasars, can you actually see that in the individual curves, or the individual light curves that it's clear from the extrema that there is a variability, that difference in the timescale? Or is it only sort of really showing up in the statistical?
It's only really showing up in the statistical analysis. I think it's similar. I know people that play around with the stock market and they claim they can see patterns, but every time I look at it, it's like, oh, it's up and down. I mean, it's a similar kind of thing, right? There's a similar kind of pattern that's in there. It's multi-scale and all that kind of stuff. And so it's the statistical coming back to some sort of property that's being picked out.
Yeah. And I mean, obviously, but, the more luminous, more distant ones tend to be more luminous than the lowest redshift ones. So getting ones where you can compare is kind of hard. Yeah. Yeah.
So just to follow up to Michael's question is, I mean, can you just plot the damping time as a function of redshift or something and see that you have, even with large error bars, you can sort of see the statistics rather than just getting a base back?
I'm pretty sure, I'm trying to remember if I did that, but you can, but again, it's in the
Dark energy in research papers not that convincing either, but then the statistics convince you, and you can sort of squint and.
Yeah, it's a similar kind of thing. The problem is you've got batches of objects that you want you've got dot, and you're saying there's a 1 plus z there, and you can sort of go, yeah, and then you've got, for the next one, they've got a different set of dots with a different 0 point effectively, and again, it's the ones over there are longer than the ones here. Actually, the picture, where are we? The thing is that I actually think if you stare at this, you can see that there is a color gradient that goes that way, right? And that color gradient is going up here. And in my head somewhere, that looks like 1 plus z. Right?
If you look at the spectrum variability, is most of this photometric variability coming from like continuum exchanges or H alpha?
This is GRI.
Right. So if you had spectra as well, and you're looking for like spectral changes as a function of time, would you expect most of the variation that you see in photometry actually from H alpha variations over time, or?
This is, well, look at the rest wavelengths.
Yeah.
This is in the most of it's in the blue and the UV.
Yeah.
Yeah. Okay. Yeah. Okay.
Okay, another.
If there's no one else. If I can just go back to your very beginning with. So obviously you say the time should dilate like 1 over 1, or 1 plus z, sorry. But the scale factor should also go like 1 over 1 plus z.
Mm-hmm.
So, I mean, what about something like velocity? For example, rather than like time? Say if you've got all quasars show an expansion of, I don't know, 10,000 kilometers a second or something in their outflows, should you be able to see the spectral line widths change with red?
I mean, this is a good question. The question is, where else can we look for 1 plus z? Because most cosmological approaches is we assume there's a 1 plus z. So you talk to anybody who does reverberation mapping, I put in a 1 plus z. If we can find a way to turn those things into standards, if you could tell me, I can tell you that this quasar intrinsically, its outflow is 4,000 kilometers per second, and then we measure it and find whatever it is, we can do the 1 plus z. But it's the calibration. How do we know intrinsically what these things are doing? So one of the things we were talking about is whether or not
They're relativistic. They're probably at the speed of light. Some fraction.
Are you sort of saying that you mentioned the time scale using reverberation mapping? So it's basically, you look for the jump in the continuum and then you look for the time delay and use that as your 1 plus.
I have no idea about this field, but it's just more thinking like spectral line widths.
Yeah.
So if you're just measuring line broadening, would you expect that to be like less at my redshift?
So the answer is yes, that it will be a 1 plus z effect. The problem that you have,
Because it's like a time dilation and a space shrinkage. Shouldn't you have 2 factors of 1 plus z?
In velocity?
yeah,
Or we're just trying to divide it length by time? We can talk later.
Yeah.
no, but again, I was talking with somebody yesterday about this very thing. Is that yes, with reverberation mapping, where there is a time scale from light from the continuum, light from the line, perfect, you can do it. The problem is that you don't know what that distance is, right? That's what you're trying to work out with reverberation mapping. And they're using that to measure the mass of the black hole. So if you could come up with a measure of the black hole mass, a dynamical mass that, quasars at high redshift or something, so you can tie that down, then maybe you've got a handle on something intrinsic to set a scale that you can measure 1 plus z with. But at the moment, it's all calibration. This is why people are arguing about whether or not you can use fast radio bursts, whether you can use gamma ray bursts, whatever, and it all boils down to comparing apples with apples.
Presumably, with reverberation mapping, you'd still expect a scaling with luminosity, so you could do it, the scatter there, obviously. So you could do it just assuming that there's a relationship with a luminosity.
Maybe.
But there's only so much time.
I was going to ask about gamma ray bursts and fast radio bursts, but I guess you've answered that one.
Well, there are people that claim that they have found a 1 plus z effect in gamma ray bursts.
You can see that out to fast distances.
Yeah, but again, what you do is you sort of say, oh, here's some gamma ray bursts. These all look really complicated. I'm going to say these guys are similar. And you say, oh, there's a 1 plus z effect in there. But there's a big push for quasars, gamma ray bursts, fast radio bursts, to standardize them, to use them as cosmological probes. And part of that will fall out of that is the measurement of 1 plus z. But at the moment, I think the dispersions in the populations are just, yeah.
Any final questions?
Can I finish on one tiny final point?
Please.
So when I published this, there was a bit of media attention, and I discovered how hard it was to explain to journalists what time dilation means. And I ended up, I had to go with Doctor Who, that it was nonlinear, non-subjective, timey-wimey stuff. They published that. Oh, it's gone. Hang on. There you go. Yeah. So I was just had to get across the concept that time is complicated, and it was like it didn't work, I think. So I don't think I convinced them.
Right, thank you. Well, let's thank Geraint again.